This is part 8 of our series of lectures on probability. And this lecture will be about Bayes' theorem and some related ideas. Basically what we're going to be looking at here is we're going to be looking at two different probability trees. We have sort of two different types of events, and the first one we're going to look at in stages. We're going to look at it where the first stage, stage 1 is done first and then stage 2, but then we can also switch it, so the tree where the stages are done in the opposite order. And so we'll see what we mean by this here in a few minutes. So let's start out with the definition of conditional probability. Now remember that conditional probability is very important in our trees because it's the conditional probabilities that are on the probabilities that are actually in the trees on every one of those edges in our tree, except for the edges out of that first vertex. So remember that the definition of the probability of A given B is the probability of A intersect B divided by the probability of B. We can solve this by multiplying both sides by probability of B, and we get probability of A intersect B is the probability of B times the probability of A given B. But notice it's also the probability of A times the probability of B given A. And so this fact that we have two different expressions for the probability of the intersection gives us two different ways to compute that, and so that gives us a lot of leverage to go back and forth here a little bit. So let's look at an example. Suppose that the probability that contestants in a statistics competition are assigned to exactly one of two judging panels. We'll call them panel A and then, well, panel not A, panel B. The probability that a contestant is assigned to panel A is 70%. So probability of A is 0.7. 65% of the contestants that were awarded an outstanding rating were judged by panel A. 20% of all the contestants who earned an outstanding rating. Let A be the event that a contestant is judged by panel A, and O be the event that a contestant earns an outstanding rating. So look what we've got here. The probability of A is 0.7. The probability of outstanding is 0.2. Since 65% of the contestants that were awarded outstanding were judged by panel A, we know that they got an outstanding, so that's given, and 65% out of those that got the outstanding were judged by panel A. So that's the probability of A given O. One of the things that we're going to be interested in is what about finding O given A? We want to kind of reverse that. So that's going to be the main focus of what we want to give. But actually, knowing just these three probabilities is enough to completely figure out every possible probability that might be concerned, that we might be concerned with in this particular example. So let's start by making out two different trees. The first tree you're going to start with, well, one of the trees you're going to start with, the first branch is going to be A and not A. And another tree, it's going to be outstanding and not outstanding are your starting points. So here we go. See if you can make that out. Press pause now. Okay, now you're back. What we mean is this. So notice that the first tree on the left, we either get outstanding or not outstanding. I'm going to use this little tilde in front, the little squiggle, to mean not. So we've got the complement of O. So O is outstanding up here, and then not O down here. Then if you get O, if you got an outstanding, it could have been judged by panel A or one of the other panels, not A. And again, if you got not outstanding, some other rating, whatever they might have been, you could be judged by panel A or not A. On the other hand, we could think of doing separating it out by whether they were judged by panel A or some other panel first. And then once you do that, so then you got A and not A for the first choice. And again, with either one of these, you still have the possibility of outstanding or not outstanding. Now go ahead and enter in the probabilities in these trees that we know. So take a second to copy this tree down. Press pause. Okay, now we're back. I'm going to back this slide up one, and these are the probabilities that we know. Go ahead and write these three probabilities in, just these three for right now. Write those actually in your tree where they go. Please do that now. Press pause. Okay, now that we're back, we want to put these three things into our tree. Where do they go? Well, here's where they go. This probability of O is the first branch here. Probability of A is the first branch on the right tree. This conditional probability of A given O is where we have A after O in our tree, and that's the top branch on the right there of the second stage. Now, just given this information, what else can we fill out in the tree? From here, what's the next step? What can we use to help us? Go ahead and press pause and fill out what you can from here. Press pause now. Okay, now that we're back, let's see what did you come up with. Did you notice that you can use the sum rule, that the probabilities out of any particular vertex coming out of that have to sum up to 1. And so we can figure out the probability of outstanding is 0.2. That was given. We can figure out the probability that's not outstanding was 80% or 0.8. Similarly, we know the probability of A given O is 0.65. Probability of not A given O has to also add up to 1 with that, so that must be 1 minus 0.65 or 0.35. Similarly, in the second tree, we know the probability of A is 0.7, so the probability of not A is 1 minus 0.7, which is 0.3. I should say 1 minus 0.7. Now, with this in mind, what else can we do? Let's see if we can compute anything else here. Go ahead and fill out what you can for the next step. Press pause now. Okay, we're back and we see that we can actually use our multiplication rule that says that the probability of O times the probability of A given O will be the probability of O intersect A, or O and A. So the fact that it's outstanding, the probability that it's outstanding and was judged by panel A is 0.2 times 0.65, or in other words 0.13. So it's 13% chance that it was both outstanding and judged by panel A. Similarly, we can multiply the probability of outstanding times the probability of not A given outstanding to give the probability that it's outstanding and not judged by panel A. That intersection probability is 0.2 times 0.35 or 0.07. Notice, by the way, that if you add this up, 0.13 plus 0.17, what do you get? Well, you get 0.2, and that's the probability of O. So the sum of all these probabilities at the end, remember these at the end are mutually exclusive, so events, so they can just be added up. And those probabilities have to, they're the only ones coming out of O, so they have to add up to the probability of O. That's an interesting little thing that we may notice as well. Okay, what else can we do now? What's the next step? Press pause now. Okay, did you notice that we can take some of these probabilities and it tells us something in the second tree? That the probabilities here at the end of the first tree are the same four, there will be 4 of them eventually. They're the same 4 numbers over here at the end of the second tree. We know 2 of them so far, and they're slightly reordered. So the probability of, this is O intersect A, this is A intersect O, same thing. So the probability that's both O and A, both outstanding and judged by panel A, is 0.13. It's also 0.13 over here in this tree because it's the same thing. Similarly, the 0.07, 7% goes down here, the probability that it's not A and outstanding. That goes down here. Now, what does that allow us to go back in and do in this second tree? Now that we have some numbers at the end and we have these at the beginning. Can we figure out something else from here? Go ahead and figure it out now. Press pause. Now hopefully you are actually pressing pause when I say so and actually figuring out the numbers in these trees as we go along. And we're using these things that I'm showing you as checks to see if you're following along. Okay? But what we know is we know these probabilities at the end and we know the probabilities here. Well, just like over here in the left tree, when we multiplied the 0.2 times the 0.65 to get the 0.13 at the end, we're going to multiply 0.7 times the probability of O given A, excuse me. Probability of A times the probability of O given A is the probability of the intersection. So if we multiply these first two probabilities to get the one at the end, that means we could take the one at the end and divide to get the one that's missing. Okay, let's go ahead and figure that out. There we go. It is 0.19 here, and then similarly down here 0.23. Go ahead and check out that division and make sure that agrees with what you came up with, or if you didn't come up with it, make sure that you understand that before we move on. Now once we have this, we want to see what else we can figure out in the second tree from this. So when I say pause, I want you to check these numbers, make sure you understand everything so far, and then go one more step in that second tree, fill out a little bit more information. Press pause now. Well, now we're back. Do you remember that these probabilities must add up to 1 coming out of each branch? Well, if you remember that, then you know that we can get these purple probabilities here. So we take 1 minus the 0.19 to get 81% for the probability of not O given A, and down here we can get 77% for the probability of not O given not A. So notice that we've actually found what we started to set out to do. We did this the last step. The probability of A given O was given to us, but we were able to find out the probability of O given A. In fact, we were able to find out the probability of O given A, not O given A, and so forth. But there's still more we can figure out. We're going to eventually figure out all the missing probabilities in this tree. Can we finish the right tree now? Go ahead and finish it out. Press pause now. Well, you know we can use that multiplication rule again. If we multiply these probabilities along the path, the 0.7 times the 0.81 is going to give us 0.57. That's the probability of not O and A. Similarly, multiply the probabilities along the bottom path, 0.3 times 0.77 to get 0.23. That's the probability of not O and not A. So those two orange probabilities we were able to give out. Now, remember how we copied the red ones from the left tree to the right tree? Can we go back now? What can we do next? Press pause now. Well, hopefully you notice that we can take the orange probabilities, copy them over to the left tree. So all four of these numbers at the end are the same. The red and the orange numbers are the same in both trees, just in a little bit different order. Actually, what we really did, the way I've set it up, is just switch the order of the two in the middle. The two on the ends are even in the same order. Now this should allow us to go back and finish out these probabilities of A given not O and not A given not O, the remaining two probabilities, using the multiplication rule again by dividing. And by doing that, go ahead and finish it out now. Press pause. Well, we finished that up here, and we find those last two probabilities are 0.71 and 0.29. So notice we only started with 3 of these probabilities. If they were the right 3, we can actually go along and figure out everything in this entire 2 trees. So now we know that we have the probability of O, the probability of A, probability not O, probability not A. We also have all the probabilities of the 4 different intersections. And then we have all the conditional probabilities. A given O, not A given O, A given not O, not A given not O, and then the other direction as well. O given A, not O given A, O given not A, not O given not A. So there are actually a bunch of probabilities here, and we were able to figure out all of them. Pretty cool, huh? Notice what we were doing is using this leverage that we have these numbers at the end are the same in both trees. And that allowed us to go back and forth. We also use a couple important facts about the trees. That is that when you come out of a vertex to the right, the probabilities on those edges have to add up to 1. We also use the fact that we can multiply probabilities along the paths to get the probabilities at the ends of the paths, which are the intersection probabilities. So if we take away some of the way we computed everything, here are all the probabilities listed out. So these are all of the probabilities that we just computed, or that were given in some cases. There's 16 different probabilities here. It's actually 20 different things written down, 20 things written down, but 4 of them are repeated in both trees. Just starting with 3 probabilities, we're able to figure out all of this. It's a really cool technique. And hopefully, the big thing that I want you to get out of this is not only the technique that we use, which can be very useful, but we also came up with reinforcing a lot of ideas about how probability trees work, and some basic properties of probabilities and conditional probabilities. Here's a two-way contingency table for the information. Notice that the shaded background numbers here in the middle are probabilities for intersections. So 13% is the probability that it's both A and outstanding, the intersection of A and O. Not A and O, not A intersected with O, that is, it's a panel that wasn't panel A and they still got an outstanding, only 7% did that. 23% were not A and not outstanding, and 57% were an A but not outstanding. And notice, since these in the middle are mutually exclusive events, in fact these 4 things actually partition the entire sample space into 4 little parts, and we see that we can add up down the columns and also across the rows. So adding up across the rows, 13% plus 7% is 20%. That's the probability of outstanding. 57% plus 23% is 80%. That's the probability of not outstanding. And then coming down the columns, 13% plus 57% is 70%, the probability of A. The probability of not A then is 7% plus 23%, which is 30%. And of course, if you add across here, across the row, 70% for 30% better be 100% or 1. And adding down the last column, 20% plus 80% better add up to 1 or 100% as well. So we can see these are 8 of the numbers that we had in the trees. What's not here is the conditional probability. So these 4 numbers in the middle here, 13%, 7%, 57, and 23%. If you look, those are the numbers here at the end, the orange and red numbers, the intersection numbers. The numbers on the front of the tree, probability A, not A, O, and not O, those things show up. The A and not A show up at the bottom row, and the last column shows up O and not O. So this has all the probabilities except for the conditional probabilities. We can also see the same information that was in the middle 4 numbers in that table, and the backgrounds are the same here, so if you want to go back and forth, you can see the 13% is the overlap of A and O, and that's the 13% here. The 7% is the part that's in O but not an A. O but not A. That's the blue background here, 7%. The 57% is A that's not O. A and not O. That's the yellow background here. The 23% then is going to be not A and not O, and that's going to be the gray part that's outside the 2 circles. And so we've got probabilities assigned to these various parts. So let's have you do an exercise that is just like the one we just did, just with some different numbers. So we're going to suppose that the probability of contestants in a statistics competition are assigned to exactly one of 2 judging panels, A or B. The probability that a contestant is assigned to panel A is 70. This should say, let's go with the bold numbers here, 0.4, 40%, and 80% or 0.8 for the outstanding. So ignore the light numbers, go with the dark numbers. 20% of the contestants earned an outstanding rating. That's not 20%, 10%. That's 0.1. Let A be the event that the contestant is judged by panel A, O the event that it earns an outstanding. So go back and create all the stuff we did with these bold numbers here. 40% for probability of A, 80% for probability of A given outstanding. Probability of outstanding is 10%. Use those numbers, complete both tree diagrams, dual trees, the 2A contingency table, and the Venn diagram showing everything that we did. So in other words, do exactly what we did in the last example with these new numbers. Press pause now. When we come back, here's what we see, and we see your numbers should agree with these. So take a look at this and check all your work against this. Press pause now. Okay, you've checked all that, so now check your 2A contingency table. Hopefully all these will check with what you have. Press pause now. And finally, let's check the Venn diagram. Should be the same as that. Okay? Now, we're going to use some of these same basic ideas with a theorem that's called Bayes' Theorem. Bayes was a mathematician that this is named after. So notice that in the preceding example, we were able to start with knowing the probability of A, the probability of O, and the probability of A given O. And among other things, we were able to find out the probability of O given A. So we were able to reverse the order of this conditional probability. And so the basic idea of comparing these two trees will be used to this to give us a result known as Bayes' Theorem. So the basic setup for Bayes' Theorem is we start with a partition of the sample space. Now what that means is we have a bunch of subsets. We'll just call them right now B1, B2, B3, whatever, up to Bn. So we got n of these sets, and none of the two of them overlap. So if you do the intersection of any of this B whatever and another B whatever, they're empty intersection if they're two different B's. B1 and B2, for example, don't intersect. B2 and B3 don't intersect. B1 and B3 don't intersect, and so forth. And then we also have that if you union them all together, it makes up the whole sample space. So we've got the whole sample space divided up into our different B's. Then we also have a different event A that overlaps some or all the sets in the partition. And what we know is we know all the conditional probabilities where we know the B's. So we know the probability of A given B1, and we know the probability of A given B2, and A given B3, and so forth and so on, up to probability of A given Bn. And we also know one more thing, and that's the probability of each of the B's. B1, we know that probability, we know the probability of B2, probability of B3, and so forth. If we know that, we can find each of the other conditional probabilities going the other direction, the probability of B sub k given A. Now, that's probably a little confusing, so let's make some sense out of this. And we're going to do this with an example. So let's use an example from medicine. There are 4 basic types of human blood based on antigens present. There's O, A, B, and then AB. That forms a partition of all human blood. O and A, you can't be both. You can't be both A and B. AB is different than either A or B. So it's not considered an overlap. So there's 4 different types. And so you put them all together, that's all the blood types there are. And we also, so it unions together to get the whole sample space. But they're also pairwise disjoint or mutually exclusive. Okay, but also blood can be either positive or negative. And really negative you can just think of as not positive. So basically we have this other set, P. So if we're going to line this up to the setup of Bayes' theorem, B1 is O, B2 is A, B3 is B, B4 is AB, and then A is our P here, using the letters I had on the previous slide. Now what we want to do is to construct the 2 related probability trees in the previous example. And what do we know? Well, we know the probability of O, the probability of A, and the probability of B, and they're given here. You can see them here in the table, in the list here. And we also know the conditional probabilities of positive given the different blood types. So probability of positive given that it's an O blood type is 0.894. Probability of positive given A, probability of positive given B, and probability of positive given AB are all known. And by the way, just in the real world here, this distribution of blood types varies for different populations around the world. This is some data, this is actual data from the US that I've pulled off of a website. So what if we want to find the probability of O given P, the probability of A given P, the probability of B given P, and the probability of AB given P? In other words, what if we know the blood type is positive? What's the probability that it's an O? Okay, we know it's positive. What's the probability it's A? We know the other direction, right? We already know that if it's an O type, the probability that it's positive is 89.4%. In other words, 89.4% of all people with O blood are actually also positive, O positive. Okay. Similarly, the probability of positive given A is 0.889. So 88.9% of the people in the United States with A-type blood are positive, that they're actually A positive. So go ahead and make a probability tree, two trees. One that starts with the branches of O, A, B, and AB, and the other one starts with branches of positive, negative. Okay, and then take the second step and fill in the probabilities that we know. Do that now. Press pause. Okay, hopefully you came up with this, and notice that we have quite a bit of information about the tree on the left, but so far nothing about the tree on the right. The tree that starts with probability with O, A, B, and AB, we know 3 of those branches right off the bat, and then we know 4 of the conditional probabilities in this tree. Now, there's 2 things I want you to do on the tree on the left. I want you to go ahead and figure out what the probability of AB is, and then the probability of O and positive. O positive, the probability of A positive, the probability of B positive, and the probability of AB positive. Go ahead and figure those out now. Press pause. Well, we know that the probabilities out of one vertex must sum to 1. So we know that these 3 probabilities here, O, A, and B, plus this one at AB, those probabilities all have to add up to 1. And so, well, you can subtract and find out that the probability of AB is 0.055. So only 5.5% of the people in the United States have AB type blood. Now, we can use the multiplication rule that says probability of O times the probability of P positive, given O, is the probability of O and positive. Probability of O positive, in other words. And so that's 0.408 times 0.894, and that gives you 0.36. Similarly, 0.317 times 0.889 is 0.28 for the probability of A positive. Probability of B positive is 0.220 times 0.937, or 0.21. And finally, at the bottom there, probability of AB of 0.055 times the 0.918 gives us a 0.05 for the probability of AB positive. Now, what does this tell us now that we've got these 4 numbers? What does this tell us about the other tree? Go ahead and fill out what you can on the other tree at this point. Press pause now. Well, notice that these 4 red probabilities for intersections are the same as the 4 values on the other tree. But now also notice that we have all of the probabilities here coming out of P. What does that allow us to do? There's one more thing we can fill in the right tree. Go ahead and do it now. Press pause. Well, remember that these 4 things here must add up to the probability of P. So if we add 0.36 plus 0.28 plus 0.21 plus 0.05, we get 0.90. So 90% of the people in the United States have positive blood. And of course, we can subtract if we want to find it to see there's only 10% that are negative. But now we can figure out what we're looking for is actually the probabilities along these branches here, on the top 4 branches on the second tier, second stage of the right tree. That's going to be the probability of O given P, the probability of A given P, probability of B given P, and probability of AB given P. You should be able to figure that out now. Go ahead and do that now, please. Press pause. Okay, did you get these numbers here? 0.4, 0.31, 0.23, and 0.06, and that's what we were looking at. We actually have enough information now, if we keep going with this, to fill out all the information in this tree that's missing. But what I wanted to focus on was finding these 4 purple numbers. And this technique right here is called Bayes Theorem. Okay? Now, let's actually write down symbolically what happened. Here's Bayes' theorem written out symbolically. So we have a partition of the sample space into n non-overlapping subsets, B1, B2, up to Bn. We also have a different event A that overlaps some or all the sets in the partition. And we know the probability of A given each of the B sub k's, and the probability of each of the B sub k's. And what we want to find is the probability of each of the B sub k's given A, the other direction. So we have a specific B sub k given A that we want to find the probability of. By definition, that's the probability of B sub k intersect A over the probability of A. That was the last step in our tree. That was, we were to find probability O given P, we took the probability of O positive, that's O intersect positive, and divided by the probability of positive. Now, we can also see that, though, to find